Ladies and gentlemen, I'm very much helped by the preceding talk because I can skip some of the topics in my talk. Now, the title of my talk is The Birth of Neutrino Astrophysics. Since the time is limited, if you want further information, please refer to this article, Observational Neutrino Astrophysics, which was printed in Physics Report some years ago. May I have the next one? Now, I am to talk about the birth of the neutrino astrophysics. But before the birth, there was a very great event which was just described by Professor Davis. It is the radiochemical work of Raymond Davis using the reaction as given there. This could be considered as a conception of the neutrino astrophysics and was the impetus for us to begin seriously working on the solar neutrinos. Next one. Now, here are the experiments I'm going to talk about. The first one is the original Kamiokande, which is what might be called imaging water Cherenkov detector, with a surface coverage of photomultiplier tubes, 20% coverage, and total mass of the water inside this detector is 3,000 tons. It costed about $3 million US. This, mind you, is a feasibility experiment on the solar neutrino detection. And the second experiment I'm going to talk about is called Super-Kamiokande, and same type of the detector, but with a better light sensitivity. That is 40% surface coverage by the photocathode. And total mass of the water is 50,000 tons. It costed about $100 million US. And this is considered to be the full-scale solar neutrino observatory. And both experiments are situated about 1,000 meters underground in Kamioka mine. The capital NDE at the end of the two experiments originally implied nucleon decay experiment. However, because of our detection of various neutrinos by these detectors, people started calling it neutrino detection experiment. I don't care which, but may I have the next slide? This is a bird's eye view of the Kamiokande detector. You can see arrays of photomultipliers on the walls and top lid, and also we have a photomultiplier at the bottom. And when we were preparing for this Kamiokande experiment, we heard that much bigger similar type experiment is being planned in the United States. We had to think very seriously about the competition with this bigger detector. Both experiments aimed for detection of certain type of photon decay. If we were aiming only for the detection of such particular type of photon decays, certainly much bigger US experiment will find it first. Then what can we do with a smaller detector? We thought very seriously about this competition, and we came to the conclusion the only possible way to compete with this bigger detector is to make our detector much more sensitive than US competitors, so that we can not only the easiest to detect proton decay mode, but also we can measure other types of proton decays, so that eventually we can say proton decays into this mode with this branching ratio and to this mode with this branching ratio and so forth, so that our experiment will be able to point the way to the possible future, what is called grand unified theory, which is a new type of theory combining strong forces, weak forces, and electromagnetic forces. We don't know this type of theory yet. Now, thanks to the cooperation of Hamamatsu Photonics, we jointly developed this very large photomultiplier tubes. I was so happy that this was successfully developed. Now, this is a Super-Kamiokande detector. Inside of this detector is shown here. You can see many more phototubes, total of about 11,000 big phototubes. Now, since not many people here are familiar with this type of detectors, I want to show you the performance of Super-Kamiokande. First example is a very slow motion picture when cosmic ray muon enters the detector and passes through to the bottom. As you know, special relativity prohibits any particle to move faster than the velocity of light in vacuum. However, in a media like water, light velocity itself is reduced to its 3/4 of its value in vacuum. Therefore, it is possible when a particle energy is very high, its velocity can exceed the velocity of light in the water, because light velocity in the water is reduced. Then what happens is that such high energy, high velocity particle in water will generate what might be called a shock wave of light, which is called Cherenkov light. It is emitted in a cone shape with the axis equal to the trajectory of the moving electrically charged particle. Next one, please. Here, it is an expanded view of a Super-Kamiokande detector. Side is cut open and extended like that. And upper lid is open like that, and the bottom is like this. It is like tin can open, okay? And each dot, it doesn't work. Each dot here represents the photomultipliers. Red light shows it received a large number of photoelectrons. The different color indicate different number of received photoelectrons. And this is a time profile of the total number of photons received, okay? Next one, please. Now, you can see particles moving this way, and Cherenkov light, wavefront is right here. Okay, next one. Now, 50 nanoseconds later, Cherenkov light traversed to this point, while the particle itself with much higher velocity already reached the bottom. You can see that particle is traveling faster than the light velocity in water. Next one, please. Now the Cherenkov light is developed, proceeded further, and you can see more at the bottom. Yeah, next one. It is fully developed now. And next one. Now, the inner detector is shown here. This is the result of outer detector, anti-coincidence layer. And you can see some signal at the exit and also at the entrance in the outer anti-coincidence layer. Now, these two examples, one by electron and the other by muon. You can see the difference in the distribution of detected photons, especially in the radial distribution of photons. You see, electron and muon are very similar particles. The only difference is that this particle has much more less mass, about 200 times heavier than this electron. It means that in traversing water, this particle suffers much less scattering, while this one gets scattered very much. Not only that, it emits gamma rays converted into electron and positron. Those low energy electrons get scattered. Therefore, the Cherenkov light emitted by those low energy particles are distributed randomly like this. By making a quantitative measurement of the radial distribution of those photons, you can make very good distinction between muon event and electron event, with a mistaking probability of less than 1%. This was a nice feature of our detector, and this feature led us to discover what is called atmospheric neutrino anomaly. I will discuss it later. Now, I'm going to talk about 4 accomplishments of old Kamiokande. Next one. The first one is this. That is astrophysical observation of solar neutrino by means of electron-neutrino electron scattering in water. By astrophysical observation, we mean information on the arrival direction of the neutrino and the arrival time of the neutrino, and also spectral information on the neutrinos. Those 3 are the requirement for the observation to be astrophysical. Now, in the case of nu-e electron scattering, since the electron rest mass is only 0.5 MeV, the incoming neutrino of, say, 10 MeV neutrino would kick electron almost in the dead forward direction. That gives, by observing this recoil electron, you can infer the arrival direction of neutrino. Okay? And also, the energy spectrum of recoil neutrino has a 1-to-1 relation to the original neutrino energy spectrum. And the timing is accurate to better than 10 nanosec. Okay? Second achievement is the observation of supernova neutrino by means of anti-electron neutrino on proton in water. And this produces E plus and neutron. And this E plus is observed by its Cherenkov price. I will show it to you later. The third accomplishment is the discovery of what is called atmospheric neutrino anomaly. That is, as I said, since we can definitely separate muon event and electron event, okay? We could measure atmospheric number ratio of nu mu over nu e very accurately by observing muon event and electron event separately. And it was discovery at more than 4 sigma, but this result was later firmly confirmed by the much better statistics data of Super-Kamiokande. I will show it to you later. Thank you. And not many people are interested in proton decay anymore, but non-observation of proton decay by this Kamiokande experiment killed well-known grand unified theory based on what is called SU5. But we go on to the next. Now this diagram was shown by the previous speaker, and I will not go into the detail here. Now this is to show the feasibility experiment by Kamiokande of observing solar neutrino with its directional information. You can see above the isotropic background, you can see accumulation of event in the direction from the sun to the earth. Next one. This is information on the energy spectrum of solar neutrinos. The expected solar standard model result should lie here. So you can see, although the shape is not very much different from the expected theoretical anticipation, but the intensity is almost 1/2. Now I go on to the observation of supernova neutrinos. Since we prepared, thanks to the collaboration of Pennsylvania State University, led by Professor Mann, we could improve the performance of our detector very much by reducing the background and so forth. And at the very beginning of 1987, our detector was calm enough to start taking data on solar neutrinos. 2 months later, we heard that there was a supernova explosion in the southern sky. So we immediately looked at our data, and then we found supernova neutrino signal very easily because our detector was already capable of taking solar neutrino data, which are much more difficult than observing supernova neutrinos, because supernova neutrinos have considerably higher average energy than solar neutrino. And not only that, those supernova neutrinos are bunched time-wise. It is shown here. This is a background, and this is the signal from the supernova neutrino. So it was very easy to detect this signal. And this observation not only gave a confirmation of the theoretical ideas on the supernova explosion, that is, gravitational collapse. For instance, not only the average energy of these things and total number, but also the time duration of about 10 seconds implies that those neutrinos are emitted from a very, very dense matter, like nucleus. Because if they were emitted from a tenuous stellar body, the time duration of the signal would have been less than 1 millisecond. But those neutrinos had to get diffused out of a very dense nucleus-like matter, so that it took seconds to get out of this surface, which made the pulse length something like 10 seconds rather than 1 millisecond. Now I come to the discussion of atmospheric neutrino anomaly. You see, when cosmic ray particle hit the atmosphere, it produces pions and kaons. Those mesons decay in tenuous air into muon and muon neutrinos. So you get 1 muon neutrino there. If the secondary muons also decay, then you get additional nu mu and nu e. So if everything proceeded this way, you get 2 nu mu against 1 nu e. So the number ratio is 2 to 1. When you go to higher energy, muons of longer lifetime than pion cannot decay. Indeed, some muons do reach our detector, as you have seen before. In this case, you don't get additional nu mu and nu e. So at high energy, this ratio is definitely larger than 2, okay? This is a result on nu mu, nu e number ratio observed by various experiments. And you can see the old Kamiokande result and Super-Kamiokande with much better statistics. And it's all around 0.5. The neutrino oscillation, this is maybe a difficult part of my talk. I try to make it understandable to the first-year undergraduate student, but this part may be a little bit more difficult. For the sake of simplicity, we consider there are only 2 kinds of neutrino in nature. Then, for instance, a wave function describing a state of a neutrino can be described by 2 independent base functions. For instance, you can take the mass matrix to be diagonal and then choose a basic vector of mass m1 and mass m2. So any neutrino state can be described by combination of psi m1 and psi m2. It is like a two-dimensional geometry. A vector can be described by its x component and the y component, okay? So this mu1 state, mu neutrino state, is a linear combination of m1 state and m2 state with a parameter theta. And two state, psi m1 and m2, have each characteristic frequency. Okay? This frequency is proportional to total energy of this state and total energy of this state. If m1 and m2 is small, then you can make this approximation, okay? So E1 minus E2, which is proportional to the frequency difference of these two states, is equal to, using this equation, is proportional to this, and you can call it delta m squared. That is m squared difference between the two states. Okay. Now, you have one parameter here, another parameter here. By using these two parameters, you can describe the oscillation of neutrino from one type to the other type. This is a result obtained by Kamiokande on atmospheric neutrino oscillation. This is the allowed region. Next one. Much bigger Super-Kamiokande established the solar neutrino observation with much better statistics. I will show it to you later. Firmly established at more than 9 sigma the non-zero masses of neutrinos and their oscillations by observing atmospheric neutrinos. We can forget about this now. Now you can see the directional observation much better than in the case of old Kamiokande. This is an isotropic background. You can see clearly the solar neutrino arrival direction, okay? Since neutrino is much more penetrating than any radiation you can think of. You see, when you have some trouble with your hand, one of your bone may be broken, you go to the doctor and get X-ray picture. And you can see inside of your hand which bone is broken and so forth. When you use neutrinos of much larger penetrability, you can see inside of the sun, okay? This is the first neutrinograph rather than photograph of the sun, okay? This is the orbit of the sun in the galactic coordinate. That sounds very nice, but if you look at this thing carefully, the size of the sun is much bigger than the size of the sun as you see by your own telescope. The reason is, of course, the neutrino angular directional accuracy is much worse than that of visible light. But you have to be patient. This neutrino astrophysics is just born. It's still in its infantile stage. Now, this is the observation of the solar neutrino energy spectrum as compared to the theoretically expected. A detailed comparison of this observed energy spectrum with the theoretical expectation gives us better information on the solar neutrino oscillation. This, by the way, is an observation of atmospheric neutrino by Super-Kamiokande. If that anomaly in the nu-E number ratio is indeed due to the neutrino oscillation, then the amount of oscillated neutrino would be different depending on the path length of neutrino from its generation to our detector. When it comes from top, it is only 20 kilometers. If it comes horizontally, it is of the order of 1,000 kilometers. If it comes from the bottom, it traveled around 13,000 kilometers. So there is a big difference in the path length. You can see the one coming from bottom is much less than the expected for a non-oscillation case. While in the case of electron event, you don't see the difference. Only in the case of muon, you see this deficiency in the large distance direction. This is a allowed region by Super-Kamiokande combined with the data of American-Canadian joint experiment in Canada, snow data. It leaves only 2 regions for the solar neutrino oscillation. Now, next one shows only one possible oscillation region when you combine not only snow and Super-Kamiokande, but also other radiochemical result. Then you are left with only one possible solution for the oscillation. Now, well, we can skip this, yeah. Now, for the sake of giving proper credit, I show this author list of supernova neutrino detection. You can see not only Japanese group, but also Pennsylvania group, collaborators of Kamiokande too. And this is the author list for atmospheric neutrino paper, and you can see many American collaborators. And this, I show you the newest result from Kamioka. Now, in Kamioka, there is the 3rd generation experiment now working. This Kamland experiment is installed in the same cave as the original Kamiokande, and this one experiment uses a liquid scintillator to measure antineutrinos, electron neutrinos, from the reactor about 200 kilometers away. And this experiment published their first result only 2 days ago. And I got this by email. Now, it is measuring anti-neutrino flux and energy spectrum, and at a distance here. And the result is shown here. And this is a region, as I indicated, for the solar neutrino oscillation in the previous slide. It fit very nicely there. So this is a confirmation of the neutrino oscillation, not for the electron neutrino, but for anti-electron neutrino. The fact that it is giving the same oscillation parameters imply that CPT theorem is not violated. And these are the parameter numbers obtained from this point. All right, thank you. Now, this is the author list of this new result. The interesting thing is that about 2/3 of the collaborators are from the United States. Now you can see that Kamioka is now considered as a mecca for neutrino research, which pleases me very much. Well, since there is still 4 minutes left, I tell you this, just for fun of you people. From the delta m squares obtained, as I have shown you, we can get a possible mass spectra of elementary particles using what is called seesaw mechanism, which is to explain the smallness of neutrino as compared with other elementary particles. Can I have next one? You get this mass spectrum. This is a logarithmic mass value. And you can see the first family, second family, and third family. When I get this, being an experimentalist, I want to have simpler scheme. I like to have this straight line. So I change the mass level a little bit. Only this much difference for the electrically charged particle makes this straight line. Automatically, neutrinos and heavy neutrinos become straight line. Now I'm happy with this. So somebody who are very good in mathematics may start thinking about mathematical operator which convert from first family to second family, and same operator changes second family to the third family, and then same operator changes third family back to the first family. That would be nice. But don't ask me the answer, because I don't know. Thank you very much for your patience.